Hello again. This is the second video for Chapter 4, where we've started talking about linear regression in the two-variable case. And last time we talked about how to estimate a regression model, and then we moved on to how to assess how well that model fits the data. And we were looking at two measures, R squared, which we did last time, and this time we're going to move on to the standard error of the regression. And we'll come to that in a second. But I want to say a little bit more about the R squared measure we talked about last time and make sure you understand intuitively exactly what that's measuring, because I'm not sure that what I said last time will do that for you. So just to recall, the definition of R squared was equal to the explained sum of squares over the total sum of squares. And we said that's also equal to 1 minus the sum of squared residuals over the total sum of squares, so that either one of these two measures would work. Let me focus on this one today and draw a picture and just make sure you understand what this is measuring. So let's recall that the explained sum of squares was equal to the sum from I equals 1 to n, where n is the sample size of the y hat, the predicted y, minus y bar squared. And the total sum of squares was equal to the sum from I equals 1 to n of the yi minus y bar squared. Make sure I use the same notation, yes. Yi minus y bar squared. And finally, the sum of squared residuals was equal to the sum from I equals 1 to n of the ui hats squared. And so those were the three pieces that were used for either one of these two formula. Okay, let's see if we can get what these formula are doing through a simple graph. I should have moved these over a little bit this way to leave more room for the graph. So let me just rewrite these things over here so we have them. ESS is the sum from I equals 1 to n of the y hat I minus y bar squared. TSS is the sum from I equals 1 to n of the yi minus y bar squared. And SSR is the sum from I equals 1 to n of the ui hat squared. So those are the residuals. Okay. Now let's take and look at a graph. Here's the xi's, here's the yi's on this graph, on this axis. And we've estimated some model. So this is y hat equals beta naught hat plus beta 1 hat x. And let me just index them with I. And there's a bunch of data points all around. I'm going to just focus on one of these data points. Let's say this one. Now let's look at that. So that's, the data are, oh, excuse me. Let me put it'll be a little bit, it doesn't change anything, but it'll be a little more intuitive if I put it above the line. So let me do this. So this is xi, and over here is yi. So that's our data point. That's the actual data point. And this is the best fitting line. There's a bunch of other data points out there as well, and this is the line that fits them all. And so this height here is yi. Up here at the line is y hat I. If I give xi to this model, it gives me back y hat I. And this distance right here is u hat for the ith observation. So in our example, we have 420 observations. Maybe this is the 53rd or the 411th or whatever one. It really makes no difference. Okay. Then somewhere in here, we don't know exactly where it is, but let me just pretend like it's here. This is y bar, okay? And so what we're trying to compare is how well we would explain the data with just a horizontal line at y bar, predicting y just with the mean, versus predicting it by using x as a variable. And so if we just had y hat equals beta naught hat, we'd get just the mean. And then we want to know how much better do we do if we add xi. So the total variance of y is the distance between here and here. So that's the total variation in y relative to y bar. So this is how much yi deviates from y bar. If I were to take this total sum of squares, which is the sum from I equals 1 to n of the yi minus y bar, that's that distance squared. If I take that total sum of squares and divide by 1 over n minus 1, that's an estimate of sigma squared y. That's an estimate of the total variance in y. So what this sum of squares is essentially just the total variation in y. That's how you estimate the variance of y. The book uses S for this instead of sigma hat, but it's the same thing. So it's the estimate of the variance in y. And so this total sum of squares is basically just the total variation in y. Now this distance here is what the explained sum of squares is. So of that total variation in y, this is the explained part. So y hat minus y bar is the explained sum of squares. Do you see that? That's the amount over and above y bar that we've explained with this model. This is what we'd explain if we just said, well, y equals y bar. This is what we explain by letting y depend upon x. This is the unexplained part. Okay, because that's the error. So our model explains this amount of variation from y bar. It doesn't explain this one. And so if we take this total, and then we do this with every point. So the total sum of squares is the total sum of the deviations from y bar. This error sum of, explained sum of squares, y hat minus yi, is the amount of that total variation that's explained. So when I take this ratio, r squared, it's the explained sum of squares over the total sum of squares. That's just a fraction of the total variance that's explained by the model. And so r squared is telling us how much of this total variance from here to here is explained by the model. So again, this is the explained variation, and this is the unexplained variation. And then we do that with every point. We square them, we add them up, and that gives us our measure of r squared. And so intuitively, that's what r squared is doing for you. So I hope that helps a little bit in explaining exactly what r squared is measuring intuitively. Okay? All right, now let's move on now to the next measure of goodness of fit, and that's called the standard error of the regression. So this is an estimate of the standard deviation of the regression error. UI. I mean, we can't observe the UIs. We can only estimate them. From those estimates, we can estimate the standard error of the regression. So what we can do is say S squared U hat, which I would be tempted to call that sigma hat squared of U hat. It's the estimated error from U hat, is equal to 1 over n minus 2 times the sum from I equals 1 to n of the U hats squared, U hat i's. What that is the sum of squared residuals over n minus 2. I'm just turning that sum of squares into an estimated variance. then the standard error of regression is just the square root of that. So the SER, the standard error of the regression, what the book calls SER, let me get the notation, which is the same as S, not S squared of U hat, is just the square root of this thing, of S squared of U hat. So the standard error of the regression is just the square root of this. So this is how you calculate it. It's n minus 2 because to get U hat, you have to estimate two things, a beta naught hat and a beta 1 hat. Remember, U hat is y minus beta naught hat minus beta 1 hat xi. Those two estimates mean you lose 2 degrees of freedom. So this is just the kind of degrees of freedom correction we talked about last time. So all this is, remember we have this scatter plot. We estimate the line y hat is beta naught hat plus beta 1 hat xi. We've got this plot of the data. The distance here are the UIs between the line and the data, gives us the UIs. So it's just a measure of how close these lines, the dots are to the line on average. It's a measure of the standard error of the data around the estimated line. So it's just the average squared error is all this is. And so it tells you that the standard deviation, and it's in the units of y. So if y is measured in dollars, it tells you how many dollars on average you are away from the line. If it's measured in test scores, it's the standard deviation in test scores. So these are measured in units of y. Unlike r squared, which is unit free. So you have to be careful to figure out whether s squared is big or small. If you're doing, measuring incomes and they're $1 million and your standard error is $1, well, that's a pretty small standard error relative to the size of yi. If you're measuring in feet and the standard error is 2 feet, then that's big relative to sort of the measurement there. And so in interpreting these, it's a little harder than r squared, because r squared is just between 0 and 1. And as you get closer to 1, we have better fit. To determine the fit here, you sort of have to normalize it in the units of y and make some interpretation. If we go to our example, the test score example, the class size test score example. So if we go back to our example and look at these two things, the test score example, remember we said that score hat was equal to 698.9 minus 2.28 times the student-teacher ratio times class times size. This was the student-teacher ratio in the model. If you measure r squared, in all packages, computer packages will give you this, it's 0.051, and the standard error of the regression is 18.6 test points. That is a large standard error, and that is a very small r squared. This is nowhere near 1.0. When this is 0, there's no association at all between size and score. And so this is a really small number. What that tells you is if you do a graph, and we've already done this, of size and score, the estimated model is negative, but the data are very, very scattered around this. You can find a negative relationship, but the strength of the association is not very strong. And this tells you that an 18.6 point standard error is very large. That would move you huge amounts in the percentile and the distribution of scores. Remember we said last time that a 4-point change in the test scores is really big. An 18-point variation is huge. So this is telling you that there's a lot of unexplained variation in test scores, that size doesn't explain all that much about test scores. Now, size still might be an important variable. It doesn't tell you this is a bad model. It doesn't tell you that size doesn't have anything to do with score. It just tells you that there's a lot more to it than just size. There's a lot of unexplained variation in the model. So it suggests there's a lot of things that are missing from this particular regression model. All right. So that's how you assess. So at this point, we should know what a regression model is. how to estimate it and how to assess whether it fits well or whether it doesn't. We haven't done hypothesis testing yet. We'll come to that soon in the next chapter, but we got a few more things to do in this one first. So let's look next at the least squares. Remember, this is a least squares estimator. This is called the OLS estimator. Beta naught hat and beta 1 hat that we've developed are called ordinary least squares estimators, sometimes just shortened to least squares. But usually you see this called OLS, ordinary least squares. So what are the ordinary or the least squares assumptions? In other words, when do we have a good model and when do we have a bad model? Can you even see that? I'm near the top of the camera there. I hope you can see this. So there's a set of assumptions that if they're satisfied, these least squares estimators have some really nice properties. They're unbiased, they're consistent, they're efficient, and the distribution of beta naught hat and beta 1 hat are both normal. Those estimators will both have normal distributions, and that'll make hypothesis testing very, very easy because we know how to use normals. If they follow some other distribution, then testing hypothesis could become very, very difficult. And so when these assumptions are satisfied, it really simplifies our life. We can use very simple estimators. When they're not as satisfied, other estimators, other ways of estimating beta naught hat and beta 1 hat become optimal, but they're harder to use. And so it makes the estimation part simple, and it makes hypothesis testing fairly simple, as we'll see. So there's three main assumptions that we need to worry about for ensuring that least squares does well. Assumption 1. This is that the conditional distribution, and I'll explain what this means in a second. Conditional distribution of the error term ui given xi has mean 0, has an expected value of 0. And so, I'm not as good at drawing at the bottom part of the board here, but let's try x, y. Let me just draw a regression line that we might have estimated. This is the true population line. This is not the estimated line. We're talking about the true errors here, not the estimated errors. Now, there's a bunch of different xi's. Let me just pick one. Here's xi. This is yi because it's the true model. But at that xi, there's a distribution of the errors. And let's assume they're normally distributed. And so the error terms, remember that the dots can be all around here. So the error terms will be basically normally distributed around this thing. So we actually go out and measure the data. The error terms will push us off the line in one direction or another. Remember, the model is yi is beta 0 plus beta 1 xi plus ui. So the actual data point xi, yi could be there, be out in the tail of the normal distribution, or it could be there, or it could be there, it could be there, it could be there. This depends on your sample draw. These are random errors. And so depending upon the error that you get, you'll get a different data, you'll get a different deviation from this line here is beta 0 plus beta 1 xi. Then you add the error on, it moves you above or below the line randomly. What's important is no matter where we measure this, those errors are mean 0. So what this is telling us is that given xi, at this particular point, maybe this is x20. So given we're at x20, for a given xi, the distribution of these errors has mean 0. So given x, the distribution, given this x, x4, given this x, x31, whatever, these things have a 0 mean distribution. Now, if the variance is the same across all these, we say it's homoscedastic. If the variance differs, some of these are very fat, some of these are very tiny. but they're all normally distributed. Some have big fat errors, but they all have mean 0. Then we say it's heteroscedastic, different variance. Homoscedastic, same variance. We're not going to make a homoscedastic assumption. So we're going to allow these errors to have different variances, but they all have to have mean 0. Okay? If that's violated, then what happens is your constant will be biased. So if errors do not have mean 0, you get biased and inconsistent, in general, estimates of beta naught and beta 1. That is, beta naught hat and beta 1 hat are biased and inconsistent. And so that's something we want to avoid because we're trying to learn the truth about the world. So we want our estimator to be correct on average. If it's wrong on average, which is what would happen if this was true, or wrong if we let the sample size go to infinity, then it's going to give us the wrong information about the world, and that's not something we want to do. So basically what generally happens if the error terms are systematically biased, so we'll just draw as upward sloping. So the peak is here, and the distance from the line is fixed, so there's a constant bias across these errors. Then what will happen is your estimated line will be biased. It'll move up and go through the 0 points. And so what will happen is you'll get a bias in this beta naught term. And sometimes you'll also get a bias in the beta 1 hat terms, and I'll come to that in a second. So this is something we want to avoid. Now, okay. Formally, what we're assuming, the mathematical thing that we're assuming is that the expected value of ui, given that xi is some particular value, like x20, this might be 10, on the x-axis, or 20 or whatever. This is class size. This just means a particular class size. Given that xi is some particular class size, is equal to 0. And it's often written in a shorthand notation. It's often written as the expected value of ui given xi equals 0. Now, one way to ensure this if you have experimental data, so you can design the experiment yourself, you can design the experiment to ensure that x and u are independent. If they're independent, then that assumption will be satisfied. So, for instance, you could assign people to 2 categories. X equals 0, which is the control, and x equals 1, which is the treatment, randomly. That ensures that x and u are independent. Whenever x and u are not independent, you get bias. And so one way to ensure that you have no bias is to treat your x's, is to choose your x's randomly, choose your treatments randomly. So if you could, what you'd want to do is go out across all the districts in the example that we have And to each district, you would assign a class size randomly. In that case, the X's and the U's would be independent for sure. But with observational data, it's often violated. This is often violated. And when it is, see, remember our thing that said maybe income matters, parental income matters, and maybe there's a correlation between parental income and class size. And when parental income goes up, you tend to see lower class sizes, so there's a correlation there. What that means is that your errors would be correlated with your x's. You wouldn't, this assumption that the expected value of ui given xi would not be 0. The expected error, given that you know you have low class size, might not be 0 in that case, and so it would be violated. So you get a correlation between the error term and the x's, because the error term would have if the model is let me be a little more careful. Score equals beta naught plus beta 1 times size plus ui, but ui has parental income in it. Well, parental income and size are correlated, so you get a correlation between ui and your xi. This is xi here. And so in that case, because parental income is correlated with class size, you don't get a 0 here. And whenever the ui is correlated with your xi, that can bias both beta naught estimator and the beta 1 estimator. And I'll show you that in a little while today when I show you the bias in beta 1 hat. And so I'll come back to this point a little bit later. But for now, you need that. Now, and see, if I were to assign the class sizes at random across the districts, then a rich district wouldn't be likely to have a low class size because I've assigned them at random. And so it could have a big class size, it could have a small class size. On average, it's going to get the average class size. So there's going to be no correlation if I assign the class sizes at random with parental income. But if I just take observational data as it comes to me, and it's true that higher income leads to lower class sizes because they can afford more teachers, then I'm going to have a correlation between my xi's and my ui's. And this assumption is not going to be true, and I will get bias. And so this is an important assumption, and it's one that is often violated in real-world data. Let me be a little bit more careful here. The expected value of ui given xi equals 0 implies that ui and xi are uncorrelated. That i.e., the correlation of xi and ui is equal to 0. But it doesn't go the other way. But correlation of xi and ui not being 0 does not imply that the expected value of ui given xi equals 0. So we can't say this, but, however, oh, I meant 0 here. Sorry. Uncorrelated does not imply that conditional mean is 0, but the conditional mean being 0 does imply they're uncorrelated. However, if xi and ui are correlated, they're not independent. If they're correlated, then we know the expected value of ui given xi does not equal 0. So anytime we can find a correlation between xi and ui, this assumption will be violated. In the example I just gave, we found a correlation between xi and ui. We said when ui tends to be big because income's big, xi tends to be small because class sizes are smaller, so we have a correlation. In that case, this assumption is necessarily violated. So the way you usually do this is you just look for correlations between ui and xi. If it's 0, it's not necessarily the case that this is true, but if it's not 0, then you know you have a problem. And so that's that. Okay, let's go to the second assumption. A little simpler, I think. Third one's really simple. Assumption 2 is that xi, yi, I equals 1, 2, up to n, must be independently and identically distributed. We call that IID. So we'll be using IID a lot in this course, and it means these are independently and identically distributed. So this is a statement about how the sample is drawn. So we want to draw randomly. Again, we need random draws from a large sample of population. So if xi is the average wage of a worker and yi is earnings, we want to know how earnings are related to average wage. We want to draw these pairs. We'll draw an individual, and he'll have these two characteristics, or she. So we draw this randomly from a population. If we draw randomly from the population, that implies IID. So the point is that we need a random draw from the population. This is often reasonable, but not always. Let me do the book's example of how this could fail. So what we have, so here's the book's example. You have 4 different organic weeding methods. Okay, and I'm going to call those X1, X2, X3, X4. And we want to know how does tomato production, yi, or just call it y, depend upon the weeding method? So what we're going to do is we're going to have 4 plots of land. One, two, three, 4. Let me just do it a little bit differently. And we're going to do this experiment a bunch of times. But if we always put X1 here, X2 here, X3 here, and X4 there, so we're going to do this a whole bunch of times. So we're going to do it over a period of 10 years. So we're going to have 40 observations. And each year we're going to apply these different weeding methods. But if we apply the same weeding method every year to the same plots of land, then we haven't randomized. And that can cause this to violate. In fact, the errors would be correlated. because this piece of land might be inferior. This land might be the best, and these might be just average. Then it's going to make it look like, then the error here is always going to be negative because this is an inferior plot of land. The error here is going to be positive because this is a really good plot of land. So when we explain it with x4, we're going to get even more because there's unobserved characteristics about the land. And so what will happen is the errors will be correlated across the experiments. Each time we do the experiment, this plot of land will tend to have a negative correlation. And so whenever we have x1 in place, we'll tend to see negative errors. Whenever we have x4 in place, we'll tend to see positive errors. These might be random, or you could tell a similar story. You know, we just have it best, second best, third best, worst, or something. I'm doing it the other way. Anyway, the point is that then there'll be a correlation between the treatment and the error. Again, we're getting a correlation in the error, and the reason is because we haven't randomized. And so you need to randomize your treatments. You need to randomize the draws from the population in order to make this true. In order to make the model work well. Okay, the last assumption, assumption 3, is that large outliers are unlikely. What this does is it makes consistency hold. And it allows us to use the normal approximation. In order to have consistency and to use the normal approximation, what you need to have is that the estimated standard errors have to converge to the true standard errors as n goes to infinity. We want that to be true, and that convergence has to be at sort of at a fixed rate. If you have large outliers, you have really fat-tailed error terms, and the book does this in terms of basically you need finite kurtosis. Remember, the kurtosis is the fourth moment. We talked about that earlier, and you need that fourth moment to be finite. If the fourth moment's infinite, then you don't get this kind of convergence. If you don't get this kind of convergence, we're relying on it. Remember that we want the t to go to a normal. With a normal, with a test statistic, it's like x bar minus mu over sigma x bar. With a t, it's x bar minus mu over s of x bar. So it's normal if we know the standard errors. It's t if we don't. But we're going to use the normal approximation to the t because it's much simpler. So in order to use that normal approximation, we need this to converge to this. If you have these big fat tails, they throw your variance estimator off because you keep getting these things pretty far from the mean, and it messes up this convergence. And so if you don't have that, if you don't have that convergence, you can't use these normal approximations, and in fact, it blows up your consistency assumptions as well. The consistency is basically that these standard errors collapse to zero. If you keep getting these really large outliers, say near infinity, you don't get that convergence to zero of the standard errors as n goes to infinity. And so for both of those reasons, basically this makes the law of large numbers apply. Mostly, this is not a problem. For instance, as long as your data have finite limits, you can't have an infinite error, you're okay. So for instance, test scores and class size have finite limits. Test scores can't go below 0, so you can't get a really big negative shock. And class size is going to be limited by some amount. It's just equal to you can have one big class, so it's equal to the population of students in the district, but it can't be infinite. And the same thing's true of test scores. There's a maximum 100% and there's a minimum 0%, and you can't go outside that range. And whenever you have those finite bounds like that, you don't have to worry about this problem. It's when you get errors way out there in the tails towards minus infinity or way out there towards positive infinity that this starts to become a problem. Okay, so why do we care? Why do we care about this? These assumptions serve two roles. One, it makes as I said earlier, if it's true, then in large samples we can use these normal approximations, and it's easy to do hypothesis tests and confidence intervals. And it also tells us that our errors are consistent, unbiased, and efficient. And so we're happy with that. If we don't have these assumptions being true, we lose those properties. We can't necessarily use the normal approximation. And you may not have consistency and unbiasedness. You may not have efficiency. And so they're important properties. The other thing is it gives us a guide. We can say, okay, if assumption 1 goes wrong, how can we correct things? If assumption 2 goes wrong, how can we correct things? If assumption 3 goes wrong, how can we correct things? And so there are ways in which we can use these assumptions to say, okay, this particular assumption is violated in a particular way, but there's a way to fix this so that that assumption is no longer a problem. In time series data, say I just look over time at GDP, and the data will tend to go in these waves as we have business cycles. Now, not exactly, but for the most part, you'll see these waves in the data. So you can estimate a model that looks like this, but the errors kind of follow a pattern, where you have recessions, recoveries, but we don't tend to see 10% unemployment followed by 4%, followed by 8%, followed by 4.1. The unemployment rate tends to be persistent and move slowly away from trend. Same with output. So what this means is that the errors are correlated, because if you have a positive error here, if you're above trend today, you're likely to be above trend tomorrow. If you're in a recession this month, you're likely to be in a recession next month. Not always, but the likelihood's there. So what happens is your errors are correlated over time. And that's a violation of assumption 2, because we haven't drawn randomly. We don't have randomness, essentially. And so this would mess up our estimates. This would cause our estimates to be inefficient in this particular case. But there's a way to take these data and transform them. You subtract off a constant times a lag, where you can estimate what the right constant is. And so I could take the data and transform them in a way that gets rid of this problem. So once I figure out what the problem is, as you'll learn in 421, then there's ways to transform the model, often to fix the problem that's causing the bias or the inconsistency or whatever it is. And so the assumptions are very useful for guiding us into how to fix things when we have problems in our model. Okay. The last thing for this chapter is the sampling distributions of the OLS estimators. What are their means and variances? I'm going to let little xi equal big Xi minus x bar, and little yi equal big Yi minus y bar. Then the OLS estimator of beta 1 hat can be written as beta 1 hat is the sum of the little xi, little yi, over the sum of the little xi squared. Remember, it's equal to beta 1 hat is the sum of the big Xi minus X bar times big Yi minus Y bar over the sum of the big Xi minus X bar squared. So we're just subbing in to this formula. Now, let AI be Xi, little xi, sorry, over the sum of the little xi's squared. Okay? Then I can write the OLS estimator as follows. Using this and this, then beta 1 hat is going to be the sum from I equals 1 to n of the AI xi. And so once AI is defined that way, I can write this. That'll give us the right answer for beta 1 hat. Yi. Now we know yi is a random variable. So a linear combination, a sum of constants times a random variable, that tells us that beta 1 hat is a random variable too, because it's a linear combination of random variables, and a combination of randomness gives you randomness. Except in some very, very special cases. And this is complicated in small samples. First of all, if yi is normal, then beta 1 hat is normal. Because a linear combination of normals is always normal. If yi has some other distribution, it's complicated in small samples. But in large samples, beta 1 hat is normal again. This is just the law of large numbers that we talked about last time. Remember we said when you calculate a mean, which is just a linear combination, it's just the sum of the x's over n. In that case, the AI is essentially 1 over n. A mean, if this is 1 over n, then the sum of the yi, you get the sum of the yi over n is a mean. And we said, well, in that case, no matter what distribution y starts with, as you let the sample size get bigger and bigger, that mean eventually turns into a normal distribution. It doesn't matter what the distribution of y is. That generalizes not just to ai being 1 over n, but ai being anything. And so long as we have a large sample and some basic regularity conditions hold, then beta 1 hat, by the law of large numbers, will also be distributed normally. So this is just nothing but the law of large numbers. That's going to be very helpful, because if beta 1 hat is normal, as it will be in large samples, and we'll argue in a little while that a sample size of 100 is usually sufficient. So let me just do it now. What is large? A sample size of 100 is usually sufficient. And in economics, that's almost always satisfied in econometric applications. Your data set is almost always at least equal to a size of 100 or bigger. And so the law of large numbers will apply in general. And so that allows us to use this normal distribution. So what are the distributions? So what are the sampling distributions of beta 0 hat and beta 1 hat? I could have done the same thing with beta naught hat, showed it was a linear combination. I mean, beta naught hat is y bar minus beta 1 hat x bar. If y is normal and beta is normal, it's the sum of normals, so beta naught's going to be normal, or we can use the law of large numbers. The same thing applies. So the first thing we can notice is that the expected value of beta naught hat is beta naught. That also tells you that it has to be consistent. And so we know it's unbiased and consistent. And the expected value of beta 1 hat is beta 1. So they're unbiased. So this is the mean of the distribution. So that's what we want. These things have some, remember, every time we draw a sample, we'll get a different value for beta 1 hat. So we're trying to figure out the relationship between earnings and age in the US. And we draw a sample of 100 people, and we estimate the regression line. We regress earnings on age, and we get a beta 1 hat. Then we go and we draw a sample of a different 100 people. We run the regression again. We're going to get a different beta 1 hat, just like we'd get a different mean every time we roll the dice 10 times of what the total sum of the, or if we roll the dice 10 times, the distribution is going to change every time. The average value that we get, we might get 10 ones, so the average is 1. We might get 10 sixes, so the average is 6. We can get all sorts of different combinations. We don't know, but every time we do it, we're going to get a different average. Every time we draw 100 people and look at their age and their earnings, we're going to get a different beta 1 hat. Those beta 1 hats that we get, though, will have a distribution. It's centered on the true value, and it's normal. That's what we're arguing. Okay. So it's centered. So on average, we're going to get the right beta 1 hat. So it's unbiased, and that's important. On average, if we do an experiment 1,000 times, we want to know that on average we're going to get the truth. So that if a bunch of different people do an experiment in the lab, and I use 100 observations, and I get one answer, you get 100 observations, get an answer, you get another one, and we average all of those, on average we're all going to be correct. So over time we'll converge to the true answer. Or it's consistent. If I let my sample size go to infinity, I'll also get the true answer. Okay, and it's normally distributed, which is going to give us a simple way to do hypothesis testing in a little bit. We need to figure out what this variance is, and I'll write that down in a second. I'm going to show this. Let's prove that this is true. And I'm going to leave this as an exercise for you. It's one of the problems. It's problem 4.7. And so I'll let you do that one as an exercise. I'm going to prove that that's true. And one reason to do this is it's going to also show us that there has to be bias. We've got a correlation between x and u. When we did the assumptions, we're making the argument essentially that whenever x and u are correlated, and there's different ways that can happen, you're going to get bias. And I'll show that right here. Okay, so let's write down the old value for beta 1 hat. So beta 1 hat was the sum of the xi minus x bar over yi minus y bar over the sum of the xi minus x bar squared. I want to take the expected value of this thing and show you that it's equal to beta 1. So let's do that. What I need to do is sub in for this yi term. So I know that yi is beta naught plus beta 1 xi plus ui, right? I know that's true. So yi minus y bar is beta naught minus y bar plus beta 1 xi plus ui. But we know that beta naught is y bar minus beta 1 x bar. Remember that? So I'm going to plug in for this here. Plug in for beta 0 using that. So I'll get yi minus y bar is beta naught minus beta naught plus beta 1 x bar plus beta 1 xi plus ui. Oops. I wrote that down wrong. Sorry about that. yi minus y bar is y bar minus beta 1 x bar, subbing for that, minus y bar, plus beta 1 xi plus ui. So yi minus y bar can be written as beta 1 times xi minus x bar plus mu I. So I can plug that in for that term. And that's what I'm going to do next. So using this fact then, I can write that beta 1 hat is equal to the sum of the xi minus x bar times, let me do it this way, times beta 1 times xi minus x bar plus ui over the sum of the xi minus x bar squared. So I just subbed in the formula we just derived for yi minus y bar. That's equal to, I can pull the beta 1 outside the sum. I'm just going to multiply this times this and this times this. That's equal to beta 1 times the sum of the xi minus x bar squared. That's those two terms, plus the sum of the xi minus x bar times ui over the sum of the xi minus x bar squared. Those are going to cancel. That will cancel that. Not here, but it does cancel there. So this will be, so beta 1 hat is equal to beta 1 plus the sum of the xi minus x bar times ui over the sum of the xi minus x bar squared. And that's an important formula. So let me just rewrite it up here so I can keep going. So beta 1 hat is beta 1 plus the sum of the xi minus x bar times ui over the sum of the xi minus x bar squared. Let me do something here. Let me write 1 over n minus 1 there and 1 over n minus 1 there. So beta 1 hat is equal to beta 1 plus, this is the covariance, the estimated covariance of x and u over the variance of x. So as long as x and u are independent, what's that covariance going to be? So if x and u are independent, as we assumed from our three assumptions, then the expected value of this is going to be 0. And so long as we have independence, the expected value of this is going to be 0, and the expected value of beta 1 hat is going to be beta 1. Let me do it more systematically. So this is just showing you, what I'm trying to show you, well, let me come back to this. So now let's just go back to this formula. So you might want to write this down again. So let me just take away the n minus 1s since they cancel. The expected value then of beta 1 hat is beta 1. The expected value of constant is a constant, plus, so long as these are independent, the expected value is the product of the expectations. So if they're independent, if our assumptions hold, the sum from I equals 1 to n of the xi minus x bar times the expected value of ui over the sum of the xi minus x bar squared. So under our assumptions, as long as these two things are independent, as long as the conditional expectation of ui given xi is 0, like we've been assuming, then we can make this move. We can bring that expectation inside. And we know these are all 0. So then the expected value of beta 1 hat is beta 1, because this has mean 0. That's one of our assumptions. The conditional given x, this expectation is 0. And so in that case, we have unbiasedness. But if xi and ui are correlated, if they're not independent, then I can't do this anymore, and the expected value of beta 1 is equal to beta 1 plus some bias. And the bias comes from this term, because this is no longer 0. And so whenever the x and u are correlated, we have a biased value for beta 1 hat. When these two things are uncorrelated, when this expectation can be 0, then this is not. And so I'll leave it to you to show the same thing for beta naught hat, that the expected value of beta naught hat is equal to beta naught. But this is how you would do it for beta 1. So 2 points here. Under our assumptions that these are basically independent, that the conditional expectation, that this has 0 mean, and these are uncorrelated, the conditional expectation of ui given xi is 0, then this will be true. When our assumptions are violated, if either this doesn't have mean 0, so if this is a number rather than 0, then we'll get a number here. Or if these things are correlated, so I can't bring that expectation across like I just did, then we're going to get some bias. But under our assumptions, importantly, beta 1 hat is unbiased. So what are the distributions of beta naught hat and beta 1? So if n is large enough, again, a large enough is, let's say, greater than 100, approximately greater than 100. Then the normal approximations hold. And beta 1 hat will be distributed, so that means is distributed normal with a mean of beta 1. We just showed that. The expected value, this is beta 1, and a variance of sigma squared beta 1 hat, where sigma squared of beta 1 hat can be written as 1 over n times the variance of xi minus x bar times ui over the variance of xi squared. We'll come up with a formula for this later that's a little bit better than this, and we'll show you what that formula looks like more explicitly. For now, we'll just leave it this way. The point is that beta 1 hat is normally distributed, it's unbiased, and it has this particular standard error, and the computer will always spit this out for you, so you don't have to calculate these very often. Again, though, we will do these formulas in the next chapter more explicitly, so I'm going to leave the actual formula for this, how you actually estimate this thing, later on. This would be one, well, we'll do it later on. Notice something. Remember I said consistency means the variance goes to 0? As n goes to infinity, what happens to the variance here? Well, this goes to 0. 1 over infinity is 0. So as n gets bigger and bigger and bigger, the distribution here gets tighter and tighter and tighter. And so for 1n, you might have a distribution that looks like this. It's centered at beta 1. As n gets larger, the distribution gets tighter and tighter and tighter until it collapses to a single point at beta 1 at infinity. So as n gets bigger and bigger and bigger, this variance gets smaller and smaller and smaller, and at infinity, the variance is 0, and you just have the true value. The other thing to notice is that as the variance of xi gets bigger, as your x's have more spread, you get a more accurate line because the variance is smaller. As the variance of xi gets bigger, its square is bigger, and that will cause the value of sigma squared beta 1 to go down. And so why is it that as the spread of the x's gets larger, as the variance of the x's gets larger, you get a more precise line? Well, just think about it. Here's x, here's y. And suppose I have 2 points that are close together, and I try to estimate a line. Exactly which line I'm going to get and what the constant should be is very, very hard to figure out. Which line, if I just have these 2 data points, this one and this one, what's the best fitting line? And there's a lot of room for this line to sort of wiggle around. And so you can have a lot of uncertainty about what the best fitting line looks like. If these dots are way far apart, then I'm much more certain about the location of my line. I get a much better, more precise estimate about what the line looks like. You can imagine if I had 2 dots, one on top of the other, I can't figure out what the constant should be at all. And so there's going to be a lot of variance in the constant. As I get these further and further apart, I get a better read on the constant. So the bigger your variance of your x's, the more precise your estimates are going to be. And you can see that because the variance of x is in the numerator of that variance. Okay, what about beta naught hat? This is a little more complicated, but beta naught hat is also distributed normally with mean beta 0 and variance sigma squared of beta naught hat. Where sigma squared of beta naught hat is equal to 1 over n times the variance of hi ui over the expected value of hi squared, where hi is 1 minus the mean of x over the expected value of xi squared times xi. So that's fairly complicated. We're not going to worry about this formula too much. Again, the computer will always spit it out for you. What's important is we know that it's normal with mean beta 0 and some variance and some standard error. And the computer will give us what this number is. We'll work a little bit with the beta 1 hat variance in the next chapter, but we're not going to do a whole lot with that particular, with this particular formula. And so this is what's important. That we know that it's distributed normally with some variance and that its mean is beta 0. And this will allow us to do hypothesis tests in the next chapter. Okay, well that ends chapter 4. Thank you, and I'll see you again soon.